Hello students, welcome to next lecture. In this session, we will be discussing switching mode regulators. So, these switching mode regulators or regulators are nothing but uh, the DC to DC converters which are used as regulator circuits. Okay, so as we know that in DC to DC converters, wherein we are controlling or varying the average DC level at the load to the desired level, whether we want the output to be higher than the input or the output to be lower than the input. So in both the case, depending on the application or the demand of the load, the DC level will be either stepped up or stepped down. So in those converters, in DC to DC converters, if we have analyzed the previous sessions and their discussion, we found that the output in the DC to DC converters had um, harmonics in them. That is, the output was not continuous. It was discontinuous and contained harmonics. So, in order to reduce the ripple content, generally the filters will be used. So, such circuit we know that they are called regulators. So, the DC to DC converters can be used as switching mode regulators to convert the DC voltage, that is the unregulated DC voltage, to get regulated DC output voltage. Okay, so such circuits are called switching mode regulators. Okay, so in this session we will be discussing the Buck type of regulator. So accordingly, in regulators as well, we have different circuits. We have Buck regulators, we have boost regulators, we have boost regulators and Cook regulators. So in Buck regulators, obviously it is similar to Buck converters, wherein it is a step down operation. That is, our output voltage will be less than the input voltage. In boost regulators, it is similar to boost converters. That is, the output voltage will be higher or greater than the input voltage. In buck boost regulators, similar to buck boost converters, based on the duty cycle, again, the same circuit can be used for stepping down or step up process. So similarly, the buck boost regulators as well. So the regulators as such, as the name indicates and we know about it, it regulates the output. Regulates in the sense it the discontinuity or the ripple content is reduced to maximum extent by the use of filters there. So by the end of this session, you will be able to describe the operation of buck regulator, and you will also learn the technique for the analysis and design of the buck regulator. So as just I have already given you some glimpse about a switching mode regulator, what it is and all. The circuit includes power switch, similar to the converter as such, and it includes the inductor, capacitor, that is the filters, and a diode to convert the DC voltages. So as mentioned, we can either step up or step down the voltage levels. All right. Um, Typically, the elements of the switching mode regulators is shown in this figure, wherein you have the chopper there. Then the output is regulated, okay, or controlled accordingly. The chopper uh, time duration, that is the duty cycle of the chopper, will be controlled. So the popular the circuit diagram for the buck regulator using a power BJT. Mainly these regulators As I said, we'll use the switching device normally as BJTs, MOSFET or IGBTs. So the circuit with the BJT is shown here, wherein the transistor is the switching device, and since it is a buck regulator, the step down operation is happening here. And as you can see, there is a LC circuit, there is a filter, the inductor and the capacitor, and the load is your resistive load. So this circuit again can be understood in two different modes. One is when the BJT is, say, switched on. So assuming that the BJT is switched on at, say, time t is equal to 0. Okay. Now the switching device is turned on. So this is the circuit where the input current, which rises, flows through the filter inductor, as you can see, the filter capacitor and the load, resistive load, right? So in mode 2, what happens? The diode will be forward biased because of the energy stored in the inductor that will be flowing through the L, C and R and the diode, right? So the current in the circuit, when the switching device, that is the BJT, is turned off, imagine it is turned off at time t is equal to t1, okay, then the energy stored in the inductor will cause, that is the current flowing in the circuit will be due to the inductor. So the same current will be flowing through the capacitor, load and the diode in mode 2. So this operation we are already familiar, and we already know how the buck converter works, right? So the waveforms are shown here. So as I mentioned, T1 is the time duration when the switch is switched on, and T2 is, sorry, when switch is turned off. Okay. So when the switching device, the transistor or the BJT is turned on, the current slowly rises, right? So the current, uh, say, it is rising linearly from level I1 to I2 during the period T1. Okay. So here IL is the current via the inductor, that is the inductor current, so which is shown here, which is varying linearly from level I1 to I2. I1 we can assume it as the minimum current and I2 as a maximum current. So it rises from I1 to I2. Is nothing but your input current. So again it is shown here from minimum level to maximum I2 for the duration T1. Okay. IC is the capacitor current. It is shown here. It is represented as IC, which is nothing but IA, which is our output current according to the circuit. Let's go back to the circuit. See, I naught or IC is nothing but the output current, which is again flowing through the capacitor. So it is represented as IA here. So VC is nothing but the voltage across the capacitor, okay, which is varying like this, which we will discuss now. So output current IA, it is shown as the continuous current. All right. So we will understand all these with the mathematical expression there. So during T2, when the switching device is turned off, the energy stored in the inductor is now dissipated. So the current flowing in the circuit will be from the inductor. So the current, it is decreasing from I2 level to I1 during the period T2 when the switching device is turned off. Okay. So this variation in the current, in the inductor current, we'll call it as delta I, which is the ripple current, which is varying from I1 to I2, and it is again varying, dissipating or decreasing from I2 to I1. So this variation, peak to peak inductor current, we'll call it as delta I. Okay. So the mathematical expression of all these waveforms we will discuss now, how it is represented. First, I hope you have understood uh, what these waveforms represent and how it is got. So this is the voltage representation wherein uh, which is the value of Vs when the switch is kept on for T1 duration, and during T2 duration the switch is turned off. Okay, so accordingly the mathematical expression, let us understand the voltage across the inductor L, it is given by EL is equal to L into di by dt. We know about this. So assuming that the inductor current rises linearly from I1 to I2 in time duration T1, so we can write it as Vs minus Va, where Vs is your input voltage and Va is the output voltage. So the difference of that is nothing but when the inductor current is rising from I1 to I2. So which is given by L into I2 minus I1 by T. Okay, which we can write it as L into delta I by T1. We will take it as equation number 1. Or we can also write the same equation in terms of T1, where T1 is equal to delta I into L from these equations divided by Vs minus A. Call it as equation number 2. Also, the inductor current falls linearly from I2 to I1 during the time duration T2. We observed that in the waveforms, right? So that we can write it as minus Va. Minus because it is dropping. The current is dropping from I2 level to I1. So we will take it as minus. Va is nothing but our output voltage, average output voltage. So we can write it as minus L into delta I by T2. So call it as equation 3. Rewriting it in terms of T2. So from this equation, T2 can be written as delta I into L divided by Va. Call it as equation number 4. So where this delta I is nothing but I2 minus I1 in both the equation, in the top two equations, delta I is equal to I2 minus I1 is nothing but peak to peak ripple current of the inductor, right? So equating the value of delta I in equation 1 and 3, observe that equation 1 and 3, substituting delta I, okay, or equating the value for delta I, we can write it as Vs minus Va into T1 by L is equal to, which we get from equation 1, yeah, Vs minus Va into T1 by L is equal to, from equation 3 we will get Va into T2 by L. I hope you are able to relate that, equating for delta I there. Okay. So from these two equations, substituting T1 is equal to KT and T2 is equal to 1 minus K into T, where K is your duty cycle. Okay. So T1, substitute it as K into T. K is your duty cycle, where duty cycle means it is nothing but T on by the total time period, right? So K is the duty cycle and T we already know that it is a chopping period, and substitute T2 as 1 minus K into T. So off period we know that it is 1 minus duty cycle, that is K. So substituting in these equation, will yield the average output voltage, that is VA. When you substitute T1 is equal to KT and T2 is equal to 1 minus KT in these two, you will get the average output voltage VA is given as K into Vs. You can substitute and verify that, though those substitutions are not shown here. You can verify that it's just a two-step substitution. So from that you will get average output voltage as VA is equal to K into Vs. Call it as equation number 5. So we are getting all the mathematical expression there for different parameters. Okay. So now assuming that this transistor what we have used is a lossless transistor switch, then the input power will be equal to the output power, right? So we can write it as VSIS is equal to VAIA. So substituting VA is equal to K into Vs here, okay, we can write it as K into Vs into IA. Just replacing VA with K into Vs. So from this relation, the average input current can be got. The average input current IS, it is given by K into IA. Where again, remember, K is nothing but the duty cycle. So call this as equation number 6. Next, now the switching period T can be expressed as 1 by F, right? The time period, the chopping period T, capital T, can be written as 1 by F, which is given by, which is nothing but T1 plus T2, that is on time period plus off time period, right? So T1 plus T2, substituting T1 delta IL by Vs minus A. Where do you get this? You get this from equation number 2. Delta IL by Vs minus A. And in terms of T2, substitute delta IL by Va. So substituting that here, so just rewriting 1 by F is equal to delta I L into Vs by Va into Vs minus A. Just making some simplification there. So from the above expression, we can write peak to peak ripple current. So delta I from this expression can be written as Va into Vs minus Va by F into L into Vs. Okay, call it as equation number 7. So this is our expression for the ripple current or the delta I, wherein it is given by Va into Vs minus Va by Fl into Vs, where F is nothing but your switching frequency. Or it can also be written as in terms of duty cycle K, substituting K and 1 minus K there, you will get that as Vs into K into 1 minus K by Fl. Call it as equation number 8. So that substitution is not shown. You can do that. Substitute duty cycle in the above expression. Now, coming to the output current, that is using the Kirchhoff current law, we can write the load current, okay, as IL is equal to IC plus I naught. Okay, let me go back to the circuit. Yeah. Okay. So here from this expression you can see the output current, it is nothing but IL is equal to IC plus I naught, right? So writing that here IL is equal to IC plus I naught. If we assume that the load ripple current delta I naught is very small and negligible, then we can write the delta IL is equal to delta IC. So the average capacitor current which flows for the time period, that is T1 by 2 plus T2 by 2, which is given by T by 2, can be written as IC is equal to, that is the average capacitor current, it is given by delta I by 4. Okay, this is the expression for the average capacitor current. Now, the capacitor voltage, it is expressed as Vc. We know that it is given by 1 by C integration of the capacitor current with respect to dt plus Vc when time t is equal to 0, right? So, the expression will come to taking the limits from 0 to t by 2. Okay, that is when the uh, voltage across the capacitor varies. So taking that limits 1 by C integration from 0 to t by 2, in place of IC you substitute delta I by 4, which we got just now from the previous expression. Integrating and substituting the limits, you will get del Vc is equal to delta IT by 8C, or you can write in terms of frequency delta I by 8FC. So call this as equation number 9. Now substituting the value of delta I from equation 7 or 8, substituting the value of delta I from this equation 7 or 8 in 9 will yield delta Vc. It is given by Va into Vs minus Va by 8LC F square Vs. Just substituting delta I there. Okay. We'll call it as equation number 10, or from equation 8 here, substituting this, okay, in equation number 9, we will get delta Vc is equal to Vs into K into 1 minus K by 8LC F square. So all these are the different terminologies what we have got from the circuit and representing them in terms of equations. Okay, here is a problem. The buck regulator in the figure shown has input voltage of Vs is equal to 12 volts. The required output voltage is Va is equal to 5 volts, and the peak to peak output voltage is 20 millivolts. The switching frequency is given as 25 kilohertz. So if the peak to peak ripple current of the inductor is limited to 0.8 amps, determine the duty cycle K, filter inductance L, and filter capacitor C. So I want you to solve this problem and submit as assignment on Saturday. Okay. So assuming that you will go through this session that is on Friday, that is 4th of December. So 5th you will be submitting this assignment, solving this problem. Okay. Please go through. If you have any doubt or clarification, you can get back. So while you go through the session, please note down all the expressions there, which will help you to calculate the different parameters. So the last two parameters, it is given to you as self-study, where you have to continue with the expression to find the values for inductor or the capacitor. That is, the design specification for inductor and capacitor is for self-study. Yes. Hoping that you will complete the assignment in time.